Did you know you can solve this crazy looking limit problem in just a minute or two? You're about to learn the power of an awesome tool known as L'Hopital's rule. So make sure to ninja kick that subscribe button and get started so that you can crush this kind of problem quickly on your AP exam. For this problem, you want to do what you normally would do for a limit. So because x is approaching 1, let's start by simply plugging in 1 for x. And for the numerator, you'll end up with 1 minus 1 divided by the natural log of 1 plus 1. And if you remember with natural logs or logs in general, the natural log of 1 here will simply be 0. And simplifying further, we're going to have 0 over the natural log of 0 plus 1. And this results in 0 divided by 0. And there's already a problem with this, right? You see it. Basically, we can't divide by 0. But the good thing is that since it's specifically 0 divided by 0, that's one of what's called the indeterminate forms. You need an indeterminate form to qualify for the ability to use L'Hopital's rule. And the beauty of L'Hopital's rule is it's basically telling you this. Going back to your original limit problem, you can solve a modified version of this problem where instead of having the top and bottom like you see, you can take the derivative of those individual functions and solve the limit with those derivatives. That way it's a simpler problem to solve. And we're going to do that just here. So I'm going to assign the numerator x minus 1 to a function I'm going to call f of x. And it's pretty trivial that the derivative of that will simply be 1. Now, the denominator gets a little bit more involved. So we're going to call that g of x. And in case you need a refresher, you want to stick around here, but you can skip forward if you've already seen the chain rule. But with the chain rule, what I'm going to do is I'm going to use a u-substitution here to make this a little bit simpler. I'm going to let u be this inner function, natural log of x plus 1, so that g of u is going to simply be the natural log of u instead. And by doing so, it makes it easier to use what's called the chain rule, because using the chain rule with a composition of functions like this and a u-substitution, what it's basically saying is you choose your outer function and you choose your inner function. And so the derivative of what you started with, g of x, is basically the derivative of this outer function where you plugged in u times the derivative of the inner function that you assigned to you. So in other words, g of u itself is going to be natural log of u. So we start by taking the derivative with respect to u. Keep in mind it's u and not x. Of natural log of u, times then the derivative with respect to x of that inner function that you assigned u to. And when we simplify this further, if you remember, the derivative of natural log of u would be 1 over u, and then times the derivative of that inner function. Now you've got a sum of terms, right? So you basically take the derivative of the natural log of x with respect to x, plus the derivative of a constant 1, which becomes 0. Now, remember, you have to put back in what u is, right? We need to have everything in terms of x. I'm going to do that back here. So now you find out that the resulting g prime of x derivative function is 1 over x times, in parentheses, natural log of x plus 1. Going back to the original problem now. So we started with this limit as x approaches 1 of two functions we're calling f of x and g of x. We can now reevaluate this using the same value of 1 we're approaching with x of f prime of x divided by g prime of x. And look how much simpler this becomes. It's pretty damn amazing. So now you have the limit as x approaches 1 of 1 divided by another fraction, because remember the derivative of g is 1 over x times natural log of x plus 1 all in parentheses. And you have this reciprocal rule you can use here, right? So that this becomes basically x times natural log of x plus 1. Because if you're doing 1 divided by something, you can just flip it. Now, look how awesome this is. When you plug in 1 here, you're not dealing with division by 0 anymore. In fact, you're just simply getting 1 times, in parentheses, the natural log of 1 plus 1, resulting in 1.